With this one we're doing this integral of x cubed times the square root of x squared plus 1. And what will be used is a combination of integration by parts as well as u sub. So first of all, it's important to be able to divide this into two parts in order for u sub to work nicely, because there is second degree x squared here, to work nicely with some of the x's that can be broken out of this x cubed term. So basically what I will do is change this to x squared times x times square root of x squared plus 1. This didn't change, but x squared times x, same like x cubed dx. So I just slightly rewrote the argument in order to be able to imagine it as two parts, namely this one and then the x squared here. Now, how will this help is basically because when we integrate this would be hard by itself, but when I have x here, I can use u sub. We will be integrating this part and this part. So basically, instead of saying that one function is x cubed and the second one is this square root, I will say that one function is x squared and the other function is this square root, including this kind of x, which will help with the u sub and with the integration. It's easier to integrate this whole thing because of u sub than to integrate just the square root itself. Alright, so what I will do now is do the integration by parts scheme as a whole. That will be the biggest building block of this process. So basically, for u, so this is the argument, just delete this thing. So the u will be the x squared and dv. So basically in integration by parts, what I'm doing is I say, well, the argument of the integral I see as u and then the derivative as two functions. First function is function u and the second function is the derivative of v. Or another way, that the first function is derivative of u and then this is just v. So basically, how I view the integrals argument when it's integration by parts is the following way. I say that it's a product of two functions where one is the derivative of that one function and the second one is that usual function. Not the same one, but another function in its usual form. So two functions where one is in its usual form in product with another function which is in its derivative form. This is how I view the argument of an integration by parts prepared integral. Now the point here is that I can rewrite this scheme when I have u and v prime. How I always rewrite it is uv, that doesn't change, minus the integral of switch the polarity of these derivatives. So if this was not and this was a derivative, then I instead have u prime times v. u prime times v. Alright? So the way the scheme of integration by parts goes is basically one is u, second is derivative of v. Then I have uv minus the integral of u prime times v. If it was the other way around, this would be same, but this would be u times v prime. But now it's the way it is. So now we're just continuing with integration by parts. U is going to stay x squared and v will be the integral of this part. So first time we see the integral of this part as a whole, explicitly here, x times x squared plus 1 in the square root, all of that dx, minus the integral of u prime, derivative of x squared, and then multiply inside the argument, the same integrals argument, by actually an integral, again the same one, because we want to get v prime into v here, into regular v. That means this will be integrated. Alright. This is one integral, and as a whole it has this dx. So it's funny that there's an integral inside the integral, but that goes as well. Just to show the entire scheme and not do it in a separate manner. I could have also already written the result of this, not to use the sigma sign, but instead I did it the way so it's explicitly all shown, all things that took place. So far what we have is x squared times the integral of this. And maybe at this point it's worth it to just carry out this integral as it's the same one like here, explicitly, and then just delete this calculation and move on. But just calculate this quickly in a separated, as a separate example. So I just take out this part just to calculate the normal function without the sigma sign, just the result of this. Well, u sub will be used here, namely x squared plus 1 will be set to u, and then du over dx will be 2x therefore. And therefore, dx will get replaced by du over 2x. So I replace x squared plus 1 by u, and dx I replace by du over 2x. So basically what I have now is x times the square root of u times du over 2x. These x's cancel out. So the result is 1/2 integral of u to the 1/2 du, which is 1/2 u to the 3/2 times 2/3, which is 2/6, which is 1/3 u to the 3/2. All right, but I have to replug in the u, which is 1/3 x squared plus 1 to the 3/2. So this will be the result of this integral as well as this integral. Now I can replace them, put them right back. So instead of this sigma sign asking for the answer, there is this exact answer being 1/3 x squared plus 1 to the 3/2 as follows. And the same goes here as well. Times 1/3. Well, the third can be put here, and x squared plus 1 to the 3/2 here as well. Alright, the c constant is left out. Now, the next thing I do is just continue with this. So what I have now is x squared over 3 times this parentheses to the 3/2 power. Then minus integral of 2/3 inside is x, the 2 first went out, x times x squared plus 1 to the 3/2 dx. Alright? And now the only thing that is left to take care of is basically this integral, while this is already basically done. There's not much way to simplify further this thing. So if we look at this integral separately, well, what does it mean? X times x squared plus 1 to the 3/2 dx. Well, I can write it as x times the square root of x squared plus 1 to the 3rd power, which is a lot. It's a big difference in the order of these terms. So what we can do here is basically again use u sub. And the thing I will do here is I will solve by u sub, setting this x squared plus 1 to u again. So du dx will again be 2x, and dx will equal to du over 2x. Therefore, from this I have x times square root of u to the 3. That simplifies things a lot. It will just be this simplified u with a fractional exponent over 2x here. Now these x's thankfully cancel out. What's left again is 1/2 the integral of u to the 3/2 du. And what this will be is 1/2 u to the 5/2 over 5/2, which is 1/5 u to the 5/2. Alright, and because 1/5 times u to the 5/2, I will substitute back this meaning of u. I have 1/5 x squared plus 1 to the 5/2. And this will be plugged in for basically this integral. So what we did is, instead of using the integration by parts a repeated time, I just used u sub right here because it worked. Alright, so what I will do here now is write it right there. Basically, that was the process. If it was quick, you can skip back in the video, move back in the video and look again. But basically what we've got so far is this thing. X squared over 3, x squared plus 1 over 3/2. Right, yielded with the u sub before, and then the second thing again with u sub. So it's a nice combination integral where both integration by parts, but also consciously u sub is combined. Alright, and this thing, what it was as an integral is basically we took this 1/3, it was in the front in the first place, so it's times 1/5 x squared plus 1 over to the 5/2 power. Alright. And then to all that I might add plus c. So what I have here is can be further simplified in some manner. What I can do is actually take back the square root notation, combine the fractions, So we have this x squared plus 1 to the third power as an entire parentheses inside second root x squared over 3 multiplying it minus 1/15 over the square root of x squared plus 1 as a parentheses all to the fifth power and some constant added to that. So this is the result. The basic idea of this case was basically a combination of both integration by parts and u substitution.